Hello everyone, and welcome back to Tech Adventure. Hope you're doing great and staying sharp in your journey of software development, embedded systems, and interview preparation. In previous videos, we covered SPI, ADCs, RTOS, top 50 real-world C and C++ interview questions, solid principles, common design patterns, and other key interview Q&A. If you missed those, be sure to check them out, especially the previous video on SPI, which includes detailed differences between SPI, I²C, and UART. Today's topic is I²C, one of the most widely used microcontroller communication protocols. We'll explore its working, addressing, modes, and applications in detail, while covering key interview questions. Let's dive in.
Imagine for a moment you're building a sleek new smart device. Maybe it's a super intelligent home assistant, managing everything from your lights to your laundry. Or maybe it's a complex piece of robotics, for precision manufacturing. Inside this thing, you're going to have loads of miniature electronic brains, tiny sensors measuring temperature, acceleration, all sorts, memory chips storing critical data, a nice vibrant display, maybe a real-time clock chip keeping perfect time.
Yeah, a whole ecosystem in there.
Exactly. And they all need to communicate, constantly swapping info, synchronizing actions, sharing data. Now picture trying to connect every single one of those directly. Its own set of wires.
Oh boy.
Think about it. Data in, data out, clock signal, chip select, power, ground for each chip. Multiply that by, dozens of components.
You'd end up with, well, a tangled mess, a spaghetti monster on your circuit board.
Totally. A nightmare.
Right.
Design, assembly, debugging.
Yeah.
It's awful.
You've absolutely hit the nail on the head there. That physical wiring complexity isn't just like messy looking. It means higher costs, bigger boards, and way, way more headaches in manufacturing and fixing things. It's just not practical for the compact electronics we rely on today.
So how do engineers tackle this? How do they untangle this digital wiring nightmare? Well, today we're doing a deep dive into a really ingenious solution called I²C. Now, you might hear it pronounced a few different ways. I've heard I²C.
I²C is common.
Or maybe I²C.
Yep, I²C too. Or sometimes even just IIC.
Right, whatever you call it. This pretty unassuming two-wire communication protocol is absolutely everywhere in our digital world, often hidden in plain sight.
And that's our mission today, really. To properly unpack this silent workhorse, we want to reveal its clever simplicity, explore why it got so popular, in countless embedded systems, and really understand the elegant mechanics behind how it handles complex two-way communication with just those two lines.
It's in your smart thermostat, managing your home's temperature, the little display on your microwave.
The motion sensor for your lights.
Or even the complex chips running your car's navigation system, the power management stuff.
Yeah.
So let's peel back the layers. Let's really get into the elegance of I²C. Okay, let's start with the basics. The core definition. At its heart, I²C, and let's maybe call it I²C or I²C for clarity. It's a synchronous serial communication protocol.
Right. Synchronous because there's a shared clock signal.
Yeah.
Everyone's on the same beat.
And serial because the data bits go one after another in a single stream, not all at once like parallel.
Precisely.
Yeah.
And it came from Philips originally, who are now NXP way back in the early 80s. But the defining feature, the revolutionary part, is just two lines. SDA for serial data and SCL for serial clock.
SDA and SCL. Got it.
Yep. SCL, the serial clock, that's the heartbeat. It synchronizes every single bit transfer with those clock pulses that all devices follow. And SDA, the serial data line, that's the information highway itself, carries the actual data bits back and forth, this two-wire design. That's fundamental to its elegance and why it's just everywhere.
So two wires for potentially lots of devices.
Yeah.
It almost sounds too simple. What are the really big advantages that made engineers jump on this?
Well, the biggest one, like you said with that tangled wire analogy, is just massively reduced wiring complexity. Yeah. Imagine you've got, say, 10 different sensors and memory chips talking to your main microcontroller. With I²C, all 10 can share the exact same two wires.
Wow, okay.
Compare that to other ways where you might need dedicated lines for each device. The savings in pins on your micro, fewer tracks on the board, simpler routing, it's huge. It really is like a party line for chips, where everyone just follows the rules for taking turns speaking.
And it connects to all sorts of different things, right? You see it all over the place.
Absolutely. It's super versatile. You find I²C linking microcontrollers to tons of peripherals, especially ones that don't need blazing speed and are physically close by. Think about your smartphone, the accelerometer checking if it's upright, the light sensor adjusting the screen, the gyro sensing rotation. A lot of those little sensors are talking back to the main processor over I²C.
Makes sense.
And beyond sensors, it's incredibly common for EEPROMs, those little memory chips storing configuration data like calibration settings or user preferences that need to stick around even with the power off. Real-time clock chips, RTCs, that keep time when the main power's down, often use I²C. And those small LCD or OLED displays in gadgets, smartwatches, industrial panels. Frequently I²C, because it needs so few pins, simplifies the whole design. It's a real workhorse for these low-speed, short-distance connections inside a system.
And you mentioned it's not just one master talking to slaves.
Mm-hmm.
It can handle multiple masters, multiple brains on the same bus.
That's right.
That sounds like it could get complicated fast, potentially chaotic, without careful thought.
It definitely adds complexity to the software side, no doubt. But that multi-master, multi-slave capability makes I²C really powerful for more advanced designs. You can have several controller devices on the same bus, plus multiple slaves. So maybe one microcontroller handles the user interface, another handles motor control.
Okay.
And both need to talk to the same EEPROM chip for settings. With multi-master I²C, they can share that bus. It needs careful firmware design to manage who talks when, which we'll get into, but it's super efficient. Avoids needing separate communication paths everywhere.
So if I²C is so great with just 2 wires, how does it stack up against other common protocols engineers might use, like SPI or UART? Where does it really shine, and when would you pick it over something else?
Yeah, that's a key decision for engineers. The main differences are in wiring, speed, and how they connect. Wiring-wise, I²C, 2 wires, potentially dozens of devices. Simple. Now, SPI, serial peripheral interface, that's also synchronous serial. But SPI usually needs at least 4 wires per device.
4 per device. Ouch.
Yep. Clock, SCK, data in, MISO, data out, MOSI, and a dedicated chip select CS for each slave. So 5 SPI devices, that's SCK, MISO, MOI, plus 5 chip selects, minimum of 8 wires right there.
Okay, that adds up fast. Pin counts matter.
They really do. It makes SPI less ideal if you have lots of peripherals and you're trying to keep pin count low.
And what about UART? I know that's often used for like basic serial comms connected to a PC for debugging, maybe?
Right, UART, Universal Asynchronous Receiver Transmitter, also uses 2 wires, transmit TX and receive RMX. And this is key, UART is strictly point-to-point, meaning it's designed for communication between just one sender and one receiver. You can't just hang multiple devices on a UART bus like you can with I²C. If you needed to talk to 10 devices with UART, you'd literally need 10 separate UART interfaces, each with its own TX and RX. That eats up microcontroller resources like crazy.
Okay, so I²C's 2-wire multi-device thing is a clear win over both SPI and UART in certain situations, especially for saving pins and wiring. What about speed and that synchronicity you mentioned?
Speed-wise, I²C is generally slower than SPI. SPI often gets higher throughput because it has separate data in and out lines, allowing full duplex, and often runs at higher clock speeds. I²C is a bit limited by its single bidirectional data line and those pull-up resistors we need to talk about, but critically, compared to UART, I²C is synchronous. It relies on that shared SCL clock line for timing.
Right, the heartbeat.
Exactly. Every data bit on SDA is timed by a pulse on SCL. Master and slave always know exactly when to sample or change the data. UART, being asynchronous, doesn't have a shared clock. Sender and receiver have to agree on a speed beforehand, like 9600 bits per second. They use start and stop bits to frame the data and resync their internal clocks for each byte.
Which sounds maybe a bit less robust.
It can be. It's simpler for point-to-point wiring, but more susceptible to timing errors if the clocks aren't perfectly matched. That shared clock in I²C is really part of its elegance, simplifying timing for everyone on the bus, even allowing for things like clock stretching if devices need more time.
Okay, that makes total sense. Two wires, shared clock, connects lots of stuff. But how does it actually work electrically? What's the secret sauce behind SDA and SCL that lets them be shared, handle data both ways on SDA without things shorting out?
Right, this is where we get into the physical layer, and it's a really clever design choice. Both SDA and SCL lines are what's called open drain, or sometimes open collector if you're dealing with older bipolar transistor tech, but the principle is the same. This is critical to understanding I²C.
Open drain. Sounds a bit technical. Can you break that down, like an analogy maybe?
Yeah.
What does it actually do?
Sure. Imagine a regular light switch. It can actively turn the light on by supplying power, or turn it off by cutting power. Push-pull, right?
Yeah.
An open drain output is more like a special switch that can only do two things.
Yeah.
It can turn the light off by pulling the wire straight down to ground,
Okay.
or it can simply let go of the wire, essentially disconnecting itself internally, letting something else control the state. It cannot actively push the wire high. It can't force the light on itself.
So it only pulls low, or it lets go. It never pushes high.
Exactly. It's like a drain. It can only open to pull water away, pull low or close to let the water level be determined by something else. Let go. It can't actively pump water and push high.
Got it. So if devices can only pull low or let go, how do the lines ever actually get high? They don't just float around, right?
No, definitely not. Floating lines are bad news in digital electronics, and that's where the absolutely essential pull-up resistors come in, often labeled RPU on schematics. Since the devices can only pull low to ground, you need these external resistors. They're connected between the I²C line, SDA or SCL, and the positive power supply, VCC. Their job is to gently pull the line back up to a high voltage state whenever no device is actively pulling it low. They ensure that when nothing's happening, or when a device wants to send a logical 1 by letting go, the line is in a stable, defined high state.
Ah, okay. Without them, it would just float and nothing would work.
Total chaos, complete communication failure. They're absolutely mandatory for I²C.
So these pull-ups are always trying to pull high, and the chips can only pull low. How does that stop the electrical fights, the conflicts we mentioned, especially with multiple masters?
This is the genius part. This open drain plus pull-up design elegantly prevents those conflicts. It makes it impossible for one device to actively drive high while another actively drives low simultaneously. In a normal push-pull output, if that happened, you'd get a direct short circuit from power to ground. Very bad, potentially damaging. Bus contention.
Right.
With open drain, if, say, a master wants to send a 1, it just lets go of the line, expecting the pull-up to make it high. But if it then reads the line and sees it's still low...
Oh, it knows someone else is pulling it down.
Precisely. It immediately knows another device is actively pulling it low, sending a 0. So the first master gracefully backs off, stops trying to transmit, and lets the other device have control. This is the core of I²C's arbitration mechanism. It lets multiple masters share the bus without collisions, ensuring stability, preventing data corruption, all without needing extra arbitration signals. It's incredibly clever.
So it's not just preventing damage, it's actively managing traffic on the shared line. And is this also why the single SDA line can handle data going both ways? Bidirectional flow?
Exactly that. Because any device can pull low, and any device can let go for the pull-up to take it high, the same physical wire works perfectly for both sending and receiving. One moment, a master is transmitting, pulling low for a 0, letting go for a 1. The next moment, it can switch its internal state to be an input and simply read the voltage level on that same line, determined by a slave that's now transmitting. This inherent flexibility is key to I²C's two-wire simplicity. It's why you get so much function from such minimal hardware.
That really is clever. Okay, so these pull-up resistors are vital, but how do you pick the right value? I imagine it's not just grabbing any resistor, and I've definitely heard engineers sweat over this.
You're absolutely right. It's not one size fits all. Choosing the right pull-up resistor value is a balancing act. It mainly depends on two things: the total bus capacitance and the desired signal rise time. Bus capacitance comes from the physical wiring. Longer cables add capacitance. It also comes from the input pins of all the devices connected to the bus, and even the PCB traces themselves. More devices or longer wires mean higher capacitance.
And that capacitance acts like, what, a hurdle for the signal?
Kind of. Think of it like a small capacitor on the line that needs to be charged up by the pull-up resistor every time the signal needs to go from low to high. More capacitance means it takes longer to charge, so the signal rises more slowly.
Okay, and there are formulas and guidelines for this, right? They may be too complex for audio.
There are, yeah. The I²C spec gives guidance. Essentially, the pull-up resistor needs to be strong enough, low enough resistance to charge that bus capacitance quickly enough for the desired speed, but not so strong that it causes other problems. We don't need the exact formula here, but the principle is higher capacitance or higher speed requires a stronger pull-up, lower resistance. In practice, you often see values like, say, 4.7 kilo ohms for standard mode, 100 kilo ohms, and maybe down to 2.2 kilo ohms, or even 1 kilo ohm for faster modes like fast mode, 400 kilobits. But these are just starting points. Always check the data sheets for your specific chips.
So what happens if you get it wrong? What are the real-world consequences if your pull-ups are too weak, meaning too high resistance?
Too weak, and your signal rise times become sluggish. Imagine trying to fill a big bucket, high capacitance, through a tiny straw, high resistance pull-up. It takes ages for the voltage to get high. This leads directly to timing violations. The devices expect the signal to be high by a certain point in the clock cycle, and it just isn't. You'll see data errors, unexpected NACK case, maybe communication just fails completely. On a scope, the rising edge looks like a slow ramp instead of a sharp step.
And the other way, too strong, like a really low resistance pull-up, pulling really hard.
If they're too strong, too low resistance, first, they draw more current all the time the line is low. This wastes power, which is bad for battery devices. More critically, it can make it too difficult for the devices to actually pull the line low. Remember, they have limited current sinking capability. If the pull-up is too strong, the device might struggle to pull the voltage all the way down to a valid 0 level. This can cause unreliable communication where nears aren't read correctly, or in extreme cases, could even potentially stress or damage the output drivers on the chips if they're constantly fighting a strong pull-up. On a scope, you might see the low level not quite reaching ground.
So that bus capacitance is a really key factor then. More capacitance equals slower rise times.
Absolutely. Higher capacitance from longer wires or more devices directly slows down those rise times. There's just more stuff the pull-up resistor has to charge. The official I²C spec actually limits the total bus capacitance, typically to 400 picofarads for standard 100 kbps operation. If you go over that, you'll likely need stronger pull-ups, with the potential downsides we just mentioned, or, more realistically, you'll have to lower your communication speed.
Which explains why I²C is usually for short distances, right? Inside a box, not across a room.
Precisely. Keep it short. Typically within a single PCB or enclosure. Meters of cable will almost certainly cause capacitance problems unless you take special measures like lowering speed drastically or using bus extenders.
Makes perfect sense. Okay, so we've got the physical wires and the clever electrical setup. Now let's talk about the actual language I²C uses. How do these devices actually converse? What's the protocol, the handshake, the data structure? How does a master tell a specific slave do this? And how does the slave answer back?
Right, this gets into the master-slave dynamics. In any I²C interaction, you always have a master and one or more slaves. The master is the boss. It initiates everything. It decides when communication starts with a start condition, sends the address of the slave it wants to talk to, dictates whether it's a read or write, provides the clock pulses, and decides when it ends with a stop condition.
And the slaves just listen.
Slaves are passive until they hear their own address called out by the master. They only speak when spoken to, essentially. They can't initiate communication on their own.
And each slave has a unique address, like a phone number, so the master knows exactly who it's calling.
Exactly. Every device on the bus needs a unique address. This is often fixed in the chip by the manufacturer, but sometimes there are address pins you can tie high or low to select from a few options, which helps avoid conflicts if you have multiple identical sensors, for instance. Many slaves also have internal register maps. Think of these like internal mailboxes or configuration menus within the chip. The master writes to specific register addresses to configure the slave, like setting a sensor's measurement range, or reads from specific register addresses to get data back, like the latest temperature reading.
So how did the addressing work? I know there's 7-bit and 10-bit addressing. What's the difference there?
Yeah, 7-bit addressing is the standard, the most common you'll find by far. It uses 7 bits for the address, which allows for up to 127 unique device addresses on one bus. Address 0 is reserved. That's usually plenty for most systems. 10-bit addressing exists as an extension. It uses a special header format to allow for, theoretically, up to 123 devices, but it's much less common. It takes longer on the bus, and frankly, not all devices even support it. So 99% of the time, you're dealing with 7-bit addressing.
Got it. 7-bit is the main one. So let's walk through the actual conversation, the handshake, step by step. How does it kick off?
It all starts with a unique signal, the start condition. This isn't just data changing, it's defined very precisely. The SDA line goes from high to low, while the SCL line is held high. This specific sequence alerts every device on the bus. Attention, bus is active, a new transaction is starting.
Okay, SDA falling while SEL is high. Unique signal. Then the master needs to say who it wants to talk to, right?
Correct. Immediately after the start, the master sends the slave's 7-bit address onto the SDA line, followed by a single read-write bit, the RW bit. This bit is crucial. RW equals 0 means the master intends to write data to the slave. RW1 means the master intends to read data from the slave. So that first byte contains both who and what direction.
And then the address slave has to respond. This is the ITT-ESEC part. Sounds important for knowing if the communication is working.
Absolutely vital. The asynchronic mechanism provides handshake and flow control. After every single byte is transmitted, the address byte, any subsequent data bytes, the receiving device takes control of the SDA line for one extra clock pulse, the 9th clock pulse. If the receiver got the byte okay and is ready for more, it sends an ACK acknowledge. It does this by actively pulling the SDA line low during that 9th clock pulse.
So low on the 9th pulse means, got it, keep going.
Exactly. But if the receiver doesn't pull SDA low during that 9th pulse, the line stays high because of the pull-up resistor. This is a NACK, not acknowledge.
And NAC canes.
It means something's wrong, or the transfer needs to stop for that byte. Maybe the address slave isn't actually on the bus, or it didn't recognize its address, and maybe the slave is busy and can't accept data right now. Or, importantly, if the master is reading data, the master itself sends a NACK after receiving the last byte it wants from the slave. Then NACK tells the slave, okay, thanks, that's all I need, you can stop sending now.
Clever. Okay, so you have the start, address, ACKs, data, more ACKs. How does the whole conversation end? How does the bus become free again?
That's done with the stop condition. It's another unique signal, essentially the opposite of the start condition. The SDA line goes from low to high, while the SCL line is held high. This clearly signals the end of the current transaction. The bus is now idle, and any other master waiting can try to initiate its own communication.
So putting it all together, what's the structure of a typical I²C data transfer, like the whole sequence?
Okay, a standard frame looks like this. Start condition, then the slave address plus RW bit. The addressed slave must respond with an ACK. Then, depending on RW, either the master sends data byte, each followed by an ACK from the slave, or the slave sends data bytes, each followed by an ACK from the master until the last byte, which gets his NACK. Finally, the master sends the stop condition. And remember, data bits are sent most significant bit, MSB first, 1 bit per SCL clock pulse. Crucially, SDA must be stable, not changing, whenever SCL is high. Changes on SDA while SCL is high are reserved for those start and stop conditions.
That makes sense. But I remember reading about something called a repeated start, often shown as senior. What's that about? Why not just use a stop and then another start?
The repeated start. This is a really neat feature, essential for certain operations. A repeated start is when the master sends another start condition without having sent a stop condition first. It looks electrically identical to a normal start, SDA low while SCL high, but the key is the context. It happens before a stop, meaning the bus never actually went idle. The master keeps control.
Okay, but why? Why keep control? Why not just stop and start again?
It's absolutely critical for atomic operations, where you need to perform multiple steps within one transaction without interruption. The classic example is reading from a specific register in a slave device, like a sensor or EEPROM. First, you need to write to the slave to tell it which register address you want to read from. Then, immediately after, you need to switch direction and read the data from that register.
Right, 2 steps. Write the address, then read the data.
Exactly. Now, if the master sent a stop condition after writing the register address, it would release the bus, even for a microsecond. In a system with multiple masters, another master could potentially grab the bus right then, before the original master could start the read part. That would break the operation. The repeated start avoids this. It lets the master send the register address, write phase, then immediately send the slave address again with the RW bit flipped to read without ever letting go of the bus. It ensures the whole write address, then read data sequence happens as one uninterrupted transaction. It prevents another master from jumping in mid-operation.
Ah, okay. That makes perfect sense. Like saying, hold on, I'm not finished, just changing direction. Essential for those multi-part commands. Let's walk through those 2 common scenarios then. Writing to a slave and reading from a slave, highlighting that repeated start in the read.
Sounds good. Let's start with writing to a slave. This one's more straightforward. 1, master sends start condition. Bus becomes active. 2, master sends slave address plus RW0 write command. 3, slave, if present and ready, sends ACK, confirms it's listening. 4, master sends the register address it wants to write to inside the slave. 5, slave sends ACK, confirms it got the register address. 6, master sends 1 or more data bytes for that register. 7, slave sends ACK after each data byte, confirms receipt, asks for more if applicable. 8, once all data is sent, master sends stop condition. Transaction ends, bus idle.
Pretty clear. Okay, now the slightly trickier one. Reading from a slave using that crucial repeated start.
Yep. Reading from a slave usually involves that 2-phase approach. 1, master sends start condition. 2, master sends slave address plus RW00 right. Wait, why right? Because first, we need to tell the slave which register we want to read from. 3, slave sends ACK. 4, master sends the register address it wants data from. 5, slave sends ACK, confirming it knows which register's data is being requested. 6, now the key part, master sends a repeat and start, SIGI, not a stop. This keeps control of the bus. 7, immediately after the SIGIR, master sends the slave address again, but this time with RW1 read. Okay, now send me data from that register I just specified. 8, slave sends ACK, confirming it's ready to send data. 9, roles flip. Master stops driving SDA and just provides SCL clock pulses. The slave now drives SDA sending data. 10, slave sends its data byte 1 bit at a time, synced to the master's clock. 11, master sends ACK after each byte it receives except the last one. This ACK tells the slave, got it, send the next byte. 12, after receiving the final byte it needs, the master sends an NACK. This tells the slave, okay, I'm done, stop sending. 13. Finally, the master sends the stop condition to end the whole transaction and release the bus.
Fantastic breakdown. That really clarifies the role of the repeated start in that read sequence. It's essential for telling the slave what to read before actually reading it, all in one go. So we've covered the logical flow. What about the rhythm, the speed, and how does it manage traffic, especially if things get busy?
Right, the rhythm. I²C isn't just one speed. It has defined speed modes offering flexibility. The baseline is standard mode at 100 kilobits per second, kbps. Then you have fast mode at 400 kilobps, which is very common these days. Going faster, there's fast plus at 1 megabit per second, mbps, and high speed mode, HS mode, reaching up to 3.4 millips.
Wow, 3.4 millips is quite a jump from 100 kilobps. Faster is usually better, right? But are there trade-offs? When would you not want to run at the highest possible speed?
That's a really important engineering trade-off. Yes, higher speeds mean faster data transfer, obviously, but they demand much stricter signal integrity. This means shorter cable runs become almost mandatory. The system gets more sensitive to electrical noise, impedance issues. Basically, everything needs to be cleaner electrically.
Because the timing windows are tighter.
Exactly. Those signal transitions from low to high, thanks to the pull-ups, need to happen much faster to be read reliably within the shorter clock periods. Bus capacitance and pull-up values become even more critical. Trying to run, say, 3.4 milliPs over even a moderately long wire or with several devices might just result in errors, while 100 kiloBps might be rock solid on the same hardware. So slower speeds are often chosen for robustness, longer distances, simpler design, or in noisy environments.
Okay, that makes sense. Now, what if a slave device is, like, busy? Maybe it's a sensor taking a measurement and it's not ready to send data when the master asks. Can it ask the master to wait, like a pause button?
Yes, it can. That's a feature called clock stretching. It's pretty clever. A slave device can physically hold the SCL clock line low temporarily. By holding SCL low, it forces the master to pause the communication. The master can't continue clocking out data or expecting data until the slave releases SCL, allowing it to go high again.
So the slave basically says, hang on a sec.
Precisely. It gives the slave time to finish whatever it's doing internally, maybe finishing an ADC conversion, writing to its internal memory. Whatever takes time before the next bit or byte needs to be transferred, the master just waits politely.
That sounds very useful for dealing with the devices of different speeds. Any catches? Does it always work?
The main catch is that not all master implementations actually support or properly handle clock stretching. Some simpler hardware masters, or ones designed only for very high-speed modes where any delay is bad, might not expect SCL to be held low by a slave. If a slave tries to stretch the clock and the master doesn't support it, the communication could hang or fail unpredictably. So you need to make sure both master and slave are okay with it if you plan to rely on it. Check the datasheets.
Good tip. So who actually sets the clock speed then? Does the master just decide, okay, we're doing 400 kiloBps now, and the slaves just have to keep up?
Pretty much, yes. The master device is the one generating the SCL pulses, so its internal configuration determines the target clock frequency. However, the actual achievable, reliable speed is heavily influenced by the physical bus characteristics, that bus capacitance and pull-up resistor combination again.
Right, the physics limit the theory.
Exactly. If you configure the master for, say, 1 MPS, but your bus has long wires and weak pull-ups, the signals won't rise fast enough. You'll get errors. The signal just gets too distorted at high speeds if the physical layer can't keep up. So the master commands the speed, but the bus physics dictate the practical limit.
Okay. Now, earlier you mentioned multi-master support. That still sounds potentially chaotic. How does I²C prevent two masters from trying to talk at the exact same microsecond and corrupting everything?
Yeah, multi-master adds complexity for the programmer, definitely. You need logic to handle potential US contention. But the protocol itself has a built-in solution. Arbitration. And this goes right back to that brilliant open drain design.
The pull lower, let go thing again?
Yeah. Exactly that. Here's how it works. If two masters happen to start a transmission at the exact same time, both send a start condition, then start sending the address byte, they both transmit and simultaneously monitor the SDA line. Let's say master A wants to send a 1. It lets go of SDA, but master B wants to send a 0. It actively pulls SDA low.
Right.
Master A tries to send 1, but reads the line and sees it's low because master B is pulling it down.
So master A knows someone else is talking and sending a 0, which wins over its 1.
Precisely. The 0 always wins because it's actively pulled low.
Yeah.
The master that detects this mismatch, tried to send high but read low, immediately knows it has lost arbitration.
And it just stops.
It stops transmitting immediately, releases the bus entirely, and goes back to listening mode, waiting for the bus to become free again, waiting for the winning master to send a stop condition. The winning master, the one whose ooze kept winning, doesn't even know a conflict happened. It just continues its transaction as normal without any data corruption. It's a completely passive, elegant way to resolve collisions without needing any extra signals. Makes multi-master possible on just those 2 wires.
That really is incredibly smart, using the electrical properties themselves to manage traffic. Okay, let's shift to the real world now. Applications, debugging, best practices.
Yeah.
Where do we most commonly find I²C in stuff we use? And what are the critical hardware things engineers need to get right for reliable operation?
Yeah, we've touched on examples, but it's worth hammering home. I²C is everywhere in embedded systems, reading environmental sensors, temp, humidity, light, pressure, accelerometers for smart homes, wearables, industrial controls, storing settings in EEPROMs, controlling power management ICs, PMICs, in laptops, phones, anything battery power to manage voltages and save power, talking to small displays, OLEDs, LCDs, and gadgets, appliances, medical devices. Its sweet spot is really those low to medium speed, short distance links inside a device where minimizing pins and wiring is key.
So, given that short distance is important, what are the practical hardware limits? Can you really not run it more than, say, a meter?
Generally, yeah, you should aim to keep it well under a meter, especially at higher speeds like 400 kilobps or more. Longer cables mean more capacitance. More capacitance means slower rise times, as we covered. If you push it too far, you either get errors or you have to drastically slow down the clock speed. If you absolutely need to go longer distances, you'd look into specialized I²C bus extenders or repeaters. These buffer the signals, maybe even convert to differential signaling for noise immunity, but they add cost and complexity. For standard I²C, keep it short and sweet on the PCB or within the enclosure.
And what about voltage levels? You often have chips running at different voltages on the same board, right? Like a 5V microcontroller talking to a 3.3V sensor. How do you handle that safely?
Very common issue and crucial to handle correctly. You absolutely cannot just connect them directly if the voltages differ significantly. You'll likely damage the lower voltage device. You need level shifters, specifically bidirectional level shifters designed for open drain protocols like I²C. These circuits safely translate the logic levels between the two voltage domains, PRG 5V and 3.3V. They often use MOSFETs cleverly arranged to allow signals to pass in either direction while respecting the voltage limits of each side. Without proper level shifting, you're asking for trouble.
Good to know. Are there any sort of variations or related technologies or ways to make I²C even more efficient?
Definitely. One you might hear about is SMBus, the System Management Bus. It's basically a derivative of I²C, built on the same foundation, but with stricter electrical specs, tighter timing, and crucially defined command protocols. You see, SMBus used a lot in PCs and servers for system monitoring, reading temperatures, fan speeds, battery status, and laptops. It's designed for that kind of critical system management role. Very similar, but with more rules than basic I²C.
Okay. And making it more efficient.
For efficiency, especially on microcontrollers, using direct memory access, DMA, with the I²C peripheral is a big win. Many micros let the I²C hardware talk directly to memory via DMA. This means you can transfer blocks of data, like reading a whole chunk from a sensor, without the main CPU having to handle every single byte interrupt.
Frees up the CPU.
Massively. The CPU just sets up the DMA transfer, tells the I²C peripheral to start, and then DMA handles moving the data between the peripheral and memory automatically. It's great for high-speed data acquisition or just reducing CPU load in busy systems.
Now, the part every engineer dreads, debugging. When I²C just stops working. What are the common nightmares and how do you wake up from them? Like, what if the bus just hangs, SDA or SEL stuck low?
Oh, yes, the dreaded bus hang. It's often a slave device that's gotten confused or stuck holding a line low. It can be really frustrating. The classic get-out-of-jail-free card for a stuck bus is the 9-clock recovery procedure. From the master, you manually toggle the SCL line low and high 9 times. This often gives the stuck slave enough clock pulses to finish whatever it was doing internally and release the SDA line. After the 9 clocks, you then manually generate a stop condition to fully reset the bus state. Doesn't always work, but it's the first thing to try.
Okay, the 9-clock trick. Good one. How do you even know what devices are supposed to be on the bus or if they're responding at the right address?
You do an IC bus scan. This is fundamental. The master basically cycles through all possible 7-bit addresses from 1 to 127, sending each address followed by the RW bit and listens for an ACK. If a device at a particular address ACKs back, you know something is alive at that address. It's perfect for discovering connected devices, checking if your hardware is wired right, or seeing if a specific chip isn't responding when it should be, often the very first debugging step.
And when you need to see exactly what's happening electrically, what tools are essential?
You absolutely need a logic analyzer or an oscilloscope. An oscilloscope lets you see the actual voltage waveforms on SDA and SCL. Is the signal clean? Are the rise times okay? Are start and stop conditions formed correctly? Is ACK and SEK happening? You can see timing issues, noise, stuck lines directly. A logic analyzer takes it a step further. It captures the digital states of SDA and SCL and potentially other signals over time. And crucially, it can decode the I²C protocol. It will show you the start-stop addresses, data bytes, ECKs, NACKs, all interpreted into human-readable format right on the screen. Immensely helpful for figuring out what data is actually being sent or received, not just the electrical shape.
So what are the usual suspects when data gets corrupted or communication is flaky? The top things engineers should check.
Okay, common culprits. 1, electrical noise. Poor grounding, noisy power supplies, running I²C lines too close to high-speed switching signals. 2, incorrect pull-up resistors, too weak gives slow rise times, too strong overloads drivers or wastes power. Get them right for your speed and capacitance. 3, excessive bus capacitance, too many devices, wires too long, slows things down, limits speed. 4, incorrect timing configuration. Master set too fast for the slave, set of hold times violated, check the data sheets. 5, simple wiring errors. SDA swapped with SCL, bad connections. Always double check the physical wiring first.
From the software side, the firmware developer, what's the typical process for setting up and using I²C on a microcontroller?
It varies between chips, but generally. You first enable the clock to the I²C peripheral itself. Then you configure the specific GPIO pins you're using for SDA and SCL to be in their alternate function mode for I²C, and critically, set them as open drain outputs. Then you configure the peripheral's registers, set the desired speed, 100K, 400K, etc. Set the addressing mode, usually 7-bit. Maybe configure interrupts or DMA if you plan to use them for efficiency.
And then actually sending or receiving data in code.
The code then follows the protocol sequences we discussed. Generate start. Send address plus RW. Check for ACK. Send a register address if needed. Check for ACK. Send or receive data bytes, checking ACK and NACK after each one. Use repeated start for reads where necessary. Send stop. It involves carefully managing the peripheral status flags, like byte transfer complete or ACK received, and potentially handling timeouts if a slave doesn't respond. Synchronization relies heavily on reacting correctly to those ACK and X signals, and respecting any timing delays specified in the slave device's data sheet.
One last tricky one. What if you have multiple sensors, say, that all have the same fixed I²C address from the factory? That sounds like a guaranteed conflict. How do developers work around that?
Yeah, that's a classic headache. If the devices don't have selectable address pins, you have a few options. The most common solution is to use an I²C multiplexer or switch IC. Think of it like a digitally controlled switch. The master first tells the multiplexer which channel or branch it wants to talk to. The multiplexer then connects the master's SDA-CL lines only to that specific branch, effectively isolating the devices on other branches. This way, you can put identical devices with the same address on different branches and talk to them one at a time.
So the multiplexer acts like a traffic director.
Exactly. Another option, if your microcontroller has multiple independent hardware I²C peripherals, some bigger ones do, you could just put the conflicting devices on separate physical I²C buses. More complex, but avoids the multiplexer.
Wow, okay. This has been an incredibly thorough deep dive into I²C or I²C or I²C. We've really gone from that elegant two-wire concept through the open drain magic, the protocol details, arbitration, all the way to real-world use and debugging. It's really impressive engineering.
It really is. It's such a foundational protocol in modern electronics. Its design is just a masterclass in solving complex communication problems, multi-device, bidirectional, multi-master, with remarkable efficiency and simplicity. Using just those 2 wires and some clever electrical tricks, engineers still appreciate its elegance today.
Absolutely. It's fascinating to think about how much data, how much control is just silently flowing through those 2 little wires in countless devices all around us. Your thermostat, your phone, your car. I²C is that hidden workhorse.
Enabling a really complex world with fundamentally surprising simplicity.
Totally. So maybe next time you look at your gadgets, you'll have a new appreciation for the quiet language being spoken inside, and perhaps wonder what other simple connections are doing extraordinary work right under our noses, making our complex world tick.
Thank you for watching. Please like, share, and subscribe to our channel for more exciting updates. Your support motivates us to create valuable content. Share your feedback or topic requests in the comments. See you in the next deep dive interview session.